Thanks for inviting me. Okay, so I think my talk is going to be a little different from the first two talks because I believe embodiment, or when you call embodied AI, it needs to have a body, and those simulators just don't have a body. It's like so I'm going to talk about more real robotics and why we need benchmarking with real robots. So I mean, I think this for a couple of first few slides is probably not for for this audience. It's mostly for classical robotics people, you know, because whenever I've gone to ICRA and I argued for benchmarking, so I've been trying this for 5-6 years at least since I started doing benchmark. Like my first paper, after that I wanted to say, okay, how do I prove it to everyone else that my first paper works? And I'm coming from computer vision. In computer vision, I know one way to prove to people that my thing works, which is benchmark. Whereas in robotics, I never had a benchmark to prove. So I believe my thing works, but I just cannot prove to the world my thing works. And that's what kind of inspired me to start going to ICRA and lots of different conferences in robotics and argue for benchmark. I think this audience, I am assuming, probably already believes benchmarking is critical. So the slides are not that critical here, but at least in ICRA, I've always found much more people are against benchmarking and so on. But still, let's play this game, right? If I show you these three robots, and like I think Rujbe was kind of, Dieter was pointing out that there are three different environments. They are doing the task of scooping. And I wanted to predict which one works the best. I'll also give you a number that this got 50%, this got 70%, this got 30%. Which one will you choose is the winner? I mean, hopefully all of you are thinking this is such a stupid question to ask, right? I mean, they're all doing different environments. We have no idea what these numbers mean, and so on. Let's try another game, another try of this. And this is something which we are seeing nowadays, a lot of these walking robots, right? I mean, and here is there are two algorithms, which are the most famous algorithms right now. I don't know, maybe there are more famous algorithms, but the two I know of nowadays, I don't work in walking. And I'm showing you these videos. Which one is the better algorithm? This is what currently robotics is, right? We show videos, we say, wow, it works. We show manipulation videos, we say, wow, it works. But then after that, it just stops. And that's why we are not basically seeing this avalanche of papers in one thing and so on, which you see a lot more in computer vision and so on. And so I think if you're a grad student, and I'm assuming a lot of you are grad student or a new faculty, and you are saying, okay, I want to build my career on something which is going to be the hottest thing and so on. And you have to decide which algorithm you want to build on. It's going to be very hard because we don't know. Does A work better, B work better, C works better, and so on. Now, to make the matters much worse, let us assume you just chose somehow magically that I want to work on algorithm B because it has more math, and I can add one more loss to the loss function, and that will make it an easy paper. But let's say you choose algorithm B and you start building on it, right? So first, what you'll do is you'll implement your own algorithm on the real robot. As we know, most of the real robotics most of these papers collect their online data. So you have to collect tens of thousands of things. Now you have a problem that you don't have the baseline, right? You don't have the baseline to compare with. So you have to now implement the same baseline on your robot, different baselines on your robot, and then collect data for them. And you keep on doing that. And this leads to the rich get richer problem. And this rich get richer problem is very well known. Labs in Stanford, Berkeley, and my own lab, CMU, maybe have very established setups. We have been publishing papers on those same setups for a long period of time. So we have the baselines already, right? And so if there's a student in my lab, he will say, I know 5 papers that have been published with this same setup. I'll just go there, and it's very easy for me to reproduce the baseline numbers because, and so on. And so that's why the established labs are publishing more and more papers every year, whereas the other people that we need, like the democratization that we need, is not happening in this field of robotics. On the other hand, we know the competing story in computer vision and NLP, right? It's just so easy. You just download the data set, right? You run your algorithm if you have it. And to get the baseline numbers, you can just copy the numbers from the table here, essentially. And so if we can bring something like this, that's what we need. And so robotics, I believe, to become successful, we'll need democratization. And to build that democratization, we will need benchmarks. And so this talk, I mean, of course, I mean, I hear everyone is probably agreeing with it, but we should do it. The next argument which I hear a lot is vision benchmarks are stupid. Look, and so this is something I hear from ICRA people a lot. They say, look, you vision people have made detection work, but if I use a detector on my robot, it will not work. And I understand vision benchmarks might be stupid, but if we create a robot benchmark, it's our opportunity to fool the vision people to do our benchmarks for us and our job for us. So here's another reason why we should build robot benchmarks, so that we can convince vision people to work on our problem rather than their problem. So benchmarking is just an easy way to scientifically compare algorithms, and that's why we should do it. Now, a good benchmark will have a wide audience that you basically lots and lots of groups can use it, and reproducible. And so Roosevelt was saying that simulator is much more reproducible, and reproducibility is critical. I completely agree. And hopefully I'll try to convince you that you can achieve reproducibility in the hardware world as well, essentially. The problem with robotics, and I think this is what everyone has pointed out, like including Dieter, is that because every lab is different, it's just hard to reproduce these numbers. The camera will be different, the hardware will be different, the lighting will be different, and so on. And that is why most of the robotics benchmarks have kind of stayed in this era of very low protocol driven, right? For example, YCB just gives you a list of 30 objects to work with, doesn't tell you what task you work on, doesn't tell you how you do the task, doesn't tell you the metric, and so on. And that's why we feel like, oh, this has very low reproducibility. So in hardware world, maybe robotics maybe benchmark is difficult. This slide I just made because I realized that people are arguing for simulation. So here is my 2 cents on why not simulation, right? So I think the biggest issue, I think, which you are asking, for example, is if you train and test on the same simulator, the learning algorithm is really good. We all know the magic of deep learning. It's going to exploit the simulator issues, some of the problems with the simulator. And now, especially, people are making these approximate bad simulators. It's much more easy to exploit something bad, essentially. And so it feels like you can basically overfit to that badness of the simulator and solve tasks with those things. And interestingly, Dieter, 2 or 3 years ago, when Aditya, who was a student in my lab, was doing his PhD thesis, and Dieter asked a really good question, which kind of took me to the core, right? And Dieter asked me, every year I see these RL papers. The way it happens is that your algorithm is like this. The baseline is always 0. And this is what the graph of every RL paper looks like. The magical thing is, next year, the one which was going like this will become this, the 0. How does this happen? Like, if it was working in 2020, getting 80%, how does in 2021 it get 0%? And I thought about it. And in fact, I went back and saw these papers. It's true that a paper which has 80% performance, by next year, it is almost getting 0% performance. Why is that happening? Because people are exploiting these simulators in a bad manner. They overfit to things. And so that's why I feel like this is kind of the core issue with the simulator as well. Then my argument, obviously, again, in real robot versus simulation, and that's what I was trying to ask Dieter essentially here is, if there was no issue, let's start with this problem. If there was no issue in engineering and stuff like that, real robot is always going to be more preferable than simulator. We have to start with this hypothesis. If this hypothesis is not true, then I think we have other issues to discuss essentially. But if a hypothesis is true that, okay, real robots is always going to be better because that's what the end task is. So if we can somehow achieve real robots, let's try to get it here. Now, the argument people say real robot is not going to work is because they said real world robots are hard. Takes too much time. I cannot publish 10 papers per year. But if you actually believe in your algorithm, 1 paper a year will give you much more impact than 10 papers a year in simulators, essentially. And you're seeing it actually happening in front of you right now. I can tell you a few algorithms which are actually showing these real world demos, and people are talking about it. Everyone is talking about them and so on. You get much more higher impact. And this is to grad students, by the way. If you are a grad student, you are still debating between simulator and real world. If you show your algorithm on a real world robot working, it's going to get you the maximum impact that you can ever get out of things. And you don't need 10 papers. You just need 1 good paper a year, as everyone says. Then people argued real robot benchmark will not work because it's too much engineering. And here my argument is, we are being kind of I don't want to use the word, but we are having this issue that communities have built much larger shared resources. We know about particle accelerators. We know about shared telescopes and so on. And all we guys cannot agree to just build a shared common robotics cloud, like where thousands of robots just test everyone's algorithm every year. That seems like we don't have the will to do it. To me, it seems a problem of more of a will than engineering issue. If all of us can agree and come together, I'm sure the government will fund it. Governments are funding particle accelerators and all these telescopes, which are much more expensive than building a shared resource of 1,000 robots to test everything out. And so, I mean, it's all feels to me, it's about the, like, for example, Dieter was saying, you had to create different environments and so on. Creating a new home environment is not that hard, right? And in fact, I'm talking about the diversity. So Roosbe will argue that, oh, you should not do real world robot because real world benchmarks or real world training will not be diverse. I argue actually opposite to it. Real world is the most diverse. If you actually want to go every home, you can just start renting 100 per night. You can actually basically get a completely new environment. How much does Roosbe need to do a very good physics environment in a simulator? He will need tens of thousands of dollars before you can get one environment with good physics. I'm not talking about shitty physics where nothing ever happens daily. I mean, I'm talking about good physics. You will need tens of thousands of dollars before a good environment can be made. Whereas in a real world, everything is open game. Every environment is open game. You can just use it, and that's the new environment that you get out for free. So to me, the diversity argument is actually against simulators rather than for simulators, essentially. So I think the last few minutes, I don't know how many minutes I have left in my argument.
You have like 10 minutes.
10 minutes, okay, good. So the last 10 minutes, I'm going to talk about two ways we have been trying to benchmark with the real robot. Again, I mean, we have been trying to convince community. We have been trying to, I feel like I'll keep trying until one of them hits, is the way. So when I'm talking about these papers, you should look at it like this. This was try one, did not hit. But I still want to tell you about what was try one. Try two, maybe, I mean, it's still in the process of knowing whether it'll hit or not. But I mean, we have to keep trying until one other thing hits. And I think that's the way I look at my benchmark research, that I'll keep on trying until everyone picks up one of the things. And this is going to be the success that I was looking for, essentially. So the first try was the result of a workshop that we had. We had a workshop on benchmarking where we invited like lots of people like Sergey, Jitendra, Stephen Charles, and everyone to just discuss about this. It was something like similar, but it was a more closed door workshop. We invited a few people. We made some discussions of what could be a good benchmark and so on. And we came up with this. So there were two resulting output. One was a rearrangement paper that I think that came out of that workshop. And the second one was this, this paper, which is benchmarking with a twist. And the idea is that we agree that recreating, so our first thought was that recreating setup is going to be hard. But even those absolute numbers probably are not meaningful. Like 50%, 60% have no meaning whatsoever. What matters is the relative ranking. Does algorithm A perform better than B and so on? So what we can do is, we can have somehow magically, if we can evaluate all the algorithms in our own labs and everyone evaluate the algorithms and send it back to us, we'll get one global algorithm ranking. The beauty of this is, because everyone is trying in their lab, you're getting the diversity of an evaluation automatically by the system. The other good part of it is, your local rankings are probably good enough for your publishing the paper, so you still want to do it. Whereas as a community, we are still developing what is going to be the successful thing here as well. And so we basically said the way we are going to look benchmark. So in computer vision, the benchmark is just the data set, the training test plates, and what you are. Here we are going to look at it differently. Here benchmark is going to be not only the training test plates, like the protocols, but also the baseline implementations. So you can download the top 5 results immediately, run them in your lab, and get the result. We are providing you the implementations of the top 5 running algorithms or top 4 running algorithms on this. So you don't have to work hard in implementing your baselines again. And so that was basically our idea, that here are the set of protocols you have to follow. Here are the baselines, the best baseline or state of the art that are running right now on this thing. Now just go and run it and send back the results to us. So it basically became very simple. The way it would run is, you basically replicate the best performing, best baselines using them from our website. You run your local experiments, and then you contribute your results to us. And because we'll get results from different labs, we'll get the diversity of evaluation, and we'll basically get some rank out of it, essentially. We had 4 different tasks that we proposed: pouring, scooping, zipping, and insertion. And the idea was, you can basically run all these 4 tasks. We gave you the list of objects to buy for training, the list of objects you need to buy for testing, and what locations would you put them to actually evaluate as well. Sorry, there are so many videos, it moves sometimes. Yeah. And so some of the interesting things that we found out was, it turns out that the behavior cloning compared to any offline RL or even closed loop behavior cloning, the open loop behavior cloning works the best. It's still the simplest thing, works the best when it comes to real robots. You can have many complicated papers with simulation results on the best thing, but it turns out the simplest behavior cloning has been the best performer on this real robot task. And the closed loop controllers, even though we can say, we can closed loop BC is like, I mean, you are taking decision every step of the action, and open is you take the whole trajectory as an output. Whole trajectory as an output. And so closed loop controllers still remain very, very hard to solve, essentially. Okay, this does not make sense. All right, so then that was the first effort. Immediately after doing it, we realized that it's going to be hard because people still need to do hardware. And our goal was to democratize. We want to have computer vision and ML people also come and do this robotics task for us, essentially. And so, but ML people and computer vision people hate hardware. As soon as you tell them that you do something on hardware, they're like, oh, we'll not do it. So that's why simulator is reigning supreme with them, because it's still software, it's fine, and so on. And so this was a very limited audience. It was not basically catching up because of that. So we went for a next try. Our next try was this, the idea of building a cloud. And this is the kind of resource I feel if we can build as a community, we can actually solve the benchmarking problem. The idea is we are going to build a cloud of tens of thousands of robots. This cloud will basically have, so you can basically do all your experiments. So if you are a lab that cannot afford a robot, or you do not want to do hardware, we will do the hardware engineering for you. This provides you the scale of engineering that we need, right? Because one engineer can handle multiple robots, and so this kind of removes the entry barrier. So if you are a computer vision person who's scared to use the hardware because writing drivers is not the thing you want to do, and so on, hopefully you can use the robot cloud, because we provide you all the things. You upload your algorithm or your data collection procedure. There is live streaming of data. You can see what kind of data it's collecting. You can modify it and re-upload it, and so on. So the best thing we've thought about robot cloud, it will remove the entry barrier. Anyone can do robotics from here on, because they don't have to worry about the hardware of the robotics. For education, this is going to be amazing. If you think about robotics as a field, only very top tier universities teach it, because it's even those universities do not give you any practical, real hands-on experience. By having this kind of a resource, you can have any tier 2 university as well use this resource to teach robotics. We'll basically work with them to create assignments and so on. And in this whole process, because everyone is working at the cloud, it's creating the largest data set, interaction data set that it could create, right? Because every data set has to be, every trajectory that is implemented on the cloud has to be open sourced and so on. So we are starting with this dream of building a cloud. I have to agree that this is very early days. We are still in the process of getting enough people to agree on it, and then basically build this as a cloud. But as a first step, to just see if we can get the community interest in it, we propose the first usage of a cloud with Chelsea, Laurel, Peter Abel, and so on, which is the train offline and test online formulation. The idea is that we'll open source an offline data set of interactions to you. You can use this to train. So this is one of the issues with any robotics benchmark, right? Because everyone is training on different data, it's hard to compare. Hopefully by having this open offline data set, now everyone is training on the same data set. So that's the first win we get, which is everyone trains on same data set. So we are comparing apples to apples for the first time. Now you basically train your favorite BC or offline RL. I mean, it's your algorithm to choose from. And you implement it. When you have a policy ready, you send the policy to us. We have the cloud running every 10 days. We run all the policies that we get. We give you a number and we send the number back to you. And in the process, we will basically be knowing which is the best performing algorithm at the end of the day. And all the data that is being created by our thing is also contributing to the open world data set, essentially. And so this idea of train offline and test online, we basically started doing it with simple 2 tasks. We said, let's start with 2 tasks and see how if there's an interest in the community. So we took the task from RB2, which is scooping and pouring, because we think that they are really good tasks for physics as well. And so we basically collected, the way we collected the offline trajectories is via VR teleoperation. We also replayed the trajectories with noise, and sometimes we did state-based BC rollout, because offline RL does not need only expert trajectories, but it also needs some bad trajectories. And so we basically created a data set with both good and bad trajectories. So our data set looks something like this. So for scooping, we have 1900 trials with 41% teleop, 33% BC, and so on. And pouring, we have around 1000 trials that we have open source essentially. And now the good part is, this is the first also step for us to try to convince vision people to do robotics benchmarks essentially. So the first way we are going to test, the first track that we are testing is, what's a good vision representation for robotics? And so the idea is you upload your own vision representation. We have our ways to train your behavior cloning algorithm using the vision representation, or like offline RL, we can choose whatever policy. And then we will test and tell you back how good your vision algorithm was, how good your visual representation was. And so we tried 5 different representations as a seed to the benchmarking. So 2 in domain that are treated with that very similar data that we have collected, and 3 kind of pre-trained, like trained from ImageNet or trained from Ego4D or whatever. And so these 5 representations are compared against each other. And so these are the 5 representations. BYOL and MoCo trained on similar data, in domain data. And then MoCo, Desert 50 is trained on ImageNet. MoCo is trained on ImageNet as well. And I think this is trained on, this is trained on, R3M is trained on Ego4D. We basically compare all these different visual representations. So here are some of the results that we are getting in visual, but, and then we basically figure out that in-domain data, of course, works better still. We are not getting the transfers from out-of-domain data that we would like to see, that like we see in computer vision yet. But still, there is hope, because out-of-domain data still seems to work reasonably okay. Not as good as in-domain, but still reasonably okay. And the way interface is very simple. All you need to do is, you need to provide us these 2 things, load model and load transform functions. So you provide those functions. And then launch these 2 scripts, which will train automatically your vision algorithm based policy, and then just send the policy and model to us, and we will evaluate it and give you the number back. So here is your opportunity. If you are a vision person, here's your opportunity to convince the robotics people to use your vision model. We also have a way to compare policy learning. So we are comparing behavior cloning, visual imitation learning, nearest neighbor, IQL, and decision transformers. In this case, we basically chose one representation, vision representation, and we combine it with different policy learning methods and compare the performance. And here are some of the numbers. Again, it turns out that behavior cloning is the most competitive, the simplest behavior cloning. So time after time, whenever we have tried, it is turning out that all the complicated RL and offline RL and other algorithms are still struggling. Behavior cloning is the winner when it comes to real world robots. And to me, that is kind of the biggest thing. In simulators, you can make anything win, but in real world, only the real thing wins. And so I think at the end of the day, so there are these other stuff like, okay, how would you use the vision things and so on. I think if you go to the website, you will be able to do it. Yeah, I want to jump since I might be out of time. All right, so again, the totobenchmark.org, you will be able to download everything to implement your vision model or your policy learning algorithm. And hopefully with this, we can have lots of people doing robotics, a lot more people doing robotics, real robots in real more and more papers, not just simulation. And think people can compare easily, much more easily. I think there are some videos of scooping and so on. And I think with that, I don't put off. Okay, I'll be happy to take questions. Yeah, go ahead.
Just a comment on the diversity thing that you mentioned, like rent and reviews. For example, if the host decided not to rent anymore, then you lose like half of your training data or your test data. So that's not a sustainable.
Is that something that does not work for computer vision? I mean, half of the images go out of use from common license, Creative Commons license. But is CoCo the thing that made it work? Probably not. I mean, we all can agree that the large scale data sets of computer vision have the same issue and they work fine. So it's all about the scale. At such high scales, some data gets lost, some data gets thing in. I don't think that can be the issue. To me, I think the bigger question is, what is the definition of diversity in robotics? Are these procedurally generated scenes, which everyone is talking about, is this diverse or is this not diverse? I mean, I don't understand. I mean, someone needs to talk about what is generalization in robotics, what is diversity in robotics. Only then I think we'll be able to better pinpoint what is worth and what is good and what is not good. I mean, I think some of these basic terms which in machine learning seem to be clear, or not machine learning, in other fields seem to be much more developed. Here, I think we are still struggling. What is a generalization? Because I have a lot of times debate about that also. Like, what is a good generalization in a robotics field of robotics as well? Yes.
In fact, top designs are very diverse, but then it also seems to me that your top designs sort of bypass these compounding errors that naturally affect some parts of computation. And also that probably explains why it was open to PDC and PDC, right? Because you have much of data in different tasks, and right, you will have actually on the previous state, and then you will need to have reader feedback. Right? So how do you have you ever considered to extend this benchmark to?
No, so I mean, we would love to extend this benchmark, and in fact, I see what you are saying. I mean, you are saying that there are no, I would not say, yeah, so sure. I mean, there are not enough compounding errors because the tasks are easy or something like that is probably what you are claiming. So I mean, I think over a period of time, I agree that maybe there will be some task where this compounding errors and then maybe closed loop will outperform open loop and so on. But at least we will agree that closed loop should not perform worse than the open loop, even in this task, right? I mean, so to me, I think that is, so I mean, what we know for that from here is that closed loop has some issues, maybe with the vision module, because when we are doing state estimation every step, if some state estimate went wrong, it's basically going to make it the whole thing go wrong. I mean, I don't know. We need to study that more. Task, I mean, we don't want to keep extending task. I mean, I think I'm all in for having as many tasks as possible, somewhere where closed loop will work better than other things. And if you have a task where you think for sure, we'll be happy to try it as well. I mean, we want to keep growing the task. I mean, I think that's an obvious statement. I mean, and it's an easy statement to make, but I mean, it will be hard to do. I agree.
How is the model of the
I think we have tried everything like LSTM2. I mean, like if you look at some of the other things like decision transformers and stuff like that, they are like, I mean, whatever the state of the art closed loop exists there. I mean, in the field right now, we have and in fact, what we were careful was we actually invited the authors themselves to do it so that they don't say that we did a bad implementation. I mean, because I mean, I agree. I mean, it's very hard to implement these things, right? I mean, because everyone has different implementations, different issues. So we want to work with authors. I mean, if you feel your algorithm is there, we want you to get multiple tries to it. If you think, because I think these are the kind of questions we want to answer. Is closed loop going to work better or not? I mean, or is this, I mean, and so, yeah, I mean, if you are interested, if you feel you have a closed loop algorithm, that should be there in the trick. We are happy to work with you and evaluate it.